Good morning. This is the second part of the lecture on computer architecture. We will briefly recollect what we looked at in the previous lecture. We started by looking at what we mean by a memory module, how a memory module can be interfaced with the processor, the various kinds of memory interleaving schemes, namely the high order and the low order memory interleaving schemes, and the memory technologies which are commonly prevalent in constructing memories. We looked at the static RAM and as well as the dynamic RAM and the problem of refreshing a DRAM and how it is slower but cheaper as compared to the SRAM. SRAMs are used in cache memories while DRAMs are used in the main memories. We also looked at the problem of designing a memory hierarchy by looking at the various metrics like cost per bit, size, access speed, bandwidth, granularity and so on. So with this introduction, we will just again look into the usual levels that are present in a cache in a memory hierarchy. The most prevalent memory hierarchies will be having one or more levels of cache followed by a main memory and the secondary memory. In this lecture, we will concentrate on the design of cache memories and the cache play related management policies. Then we will look at in the next lecture the virtual memory design, and then we will take up the IO devices. So the organization of the lecture is, after having a brief look at the memory hierarchy, we will get into the cache memory design. We will look at the major cache organization schemes, which are the direct mapping, associative mapping and set associative mapping. We will also look at the various cache policies, management policies like the replacement policy, fetch policies and so on, different kinds of cache misses that can occur and how we can reduce those misses, and also the cache write policy. So briefly recalling, the memory hierarchy has a pyramidal structure. So we put memories from various technologies with different characteristics and build a hierarchy so that it meets our design requirements. Okay, here we have seen various levels of memory. The level 0 is the one which is as a part of the CPU itself. It has got the registers, and there are various levels, okay, some of which we call it as the cache memory. In this case, the level 1 and level 2 or cache memories, which may be on chip cache or on the board cache. And then we will have the main memory. L3 is the main memory. Then we will have secondary memories, may be distributed into 2 or more levels. You should see that the registers on the on chip cache use the SRAM technology and therefore they are very fast. Then the level 2 memory, the level 2 cache may also use SRAM technology, and the contents of the level 1 memories will be present in the L2 memory, and a part of the L2 memories data, okay, will be brought to the L1 memory, and L3 memory is the main memory where the program resides and get executed. It uses the dynamic RAM technology generally to keep up the cost in taking cost into consideration. Then the local storage devices and the remote secondary access devices in a distributed system form the secondary memory. You would see that as we go towards the processor, as you can see here, the memories are becoming smaller, they are becoming faster, but they are costlier. The cost per bit of the memory is larger. But as you go out, that is away from the processor, you will have larger memories, but they are slower memories, but they are cheaper memories. Coming to the cache memory, you may have 2 ways in which cache memory can be introduced to meet the speed gap between the processor and the main memory. In one level cache, then the CPU and the main memory is being separated by introducing a level of cache which acts as an mediator between these the processor and the main memory. We will have blocks of words being accessed from the main memory and loaded into the cache, and whenever the CPU makes an access, it first checks into the cache and then retrieves the word. The access between the cache and the CPU is fast, as compared to it the access from the main memory is slower. You can also have multiple levels of cache. In this bottom figure we will show 3 levels of cache. So the level 1 L1 memory, cache memory, is the fastest. It is followed by the level 2, which is fast but not as fast as the L1. Then we will have a less fast memory, which is the L3 memory. But as you would see that as we go from L1 to L2 to L3, the size of the cache memory increases. So more data can be stored in L3 as compared to L2 and so on. Finally, we have the slow main memory being connected to the L3. In the main memory, all the data that would be required by the program are stored. To give an example, you may have a 3 level or 2 level, in this case, cache memory design, okay, and the typical values of the size, speed and the cost are given here. Within the processor you have got the registers and the level 1 memory. The level 1 memory itself may be divided into 2 parts, okay. The data memory, data cache and the instructions cache can be separated out. So you will have what is called the split cache, a separate data cache and separate instruction cache. We will later see the advantages of having a split cache, because it doubles the bandwidth of the level 1 cache, and we can employ different policies to manage these 2 caches, because the data and instruction have got different characteristics. Then the level 2 cache is usually a unified cache, which means both data and instructions are intermixed and stored in this level 2 cache, followed by the main memory and followed by the secondary memory, which is the disk. So in terms of this size, you would see that the registers may be storing about maximum of 200 bytes, okay. That depends upon a fewer number of 32-bit registers. Then the size of the level 1 cache may be 8 to 64 KB, as compared to that the L2 cache may be of size 1 to 4 MB, whereas the main memory may be of size 128 or 256 or even 512 MB, and the secondary memory will be a very large one, 30 GB or 500 GB or even 1 TB. Coming to the speed, the cache memories and the registers access speed is of the order of 1 to 5 nanosecond, 3 nanosecond in this case, okay, whereas the L2 cache memory would have larger one, maybe of the order of 10 nanosecond. As compared to that, the access speed of the main memory is 10 times more than that of the L2 cache. So it is 60 nanosecond as compared to the 6 nanoseconds, whereas the access time for the secondary memory is much larger, the order of 1000 times slower than that of the main memory. You can also look at the cost per bit. You will see that the secondary storage devices are much cheaper in terms of the dollars or rupees for storing a bit or 1 MB. So this arrow mark shows that as you move out of the processor, you get larger memories which are slower but which are cheaper. Okay. So to give an example, we will look at the way the memory is organized for the Intel Pentium processor. So here registers have some place to store the data, and we have got 2 on-chip memory. This is a split memory, L1 data and L1 instruction. The speed is, it takes 1 clock period or 1 cycle to fetch value from the L1 data memory. It is a 16 kilobyte memory. We will see it is a 4-way set associative memory following the write through policy, and the total size of the block is 32 bytes. It will become more clear what we mean by line, what we mean by associativity and so on. When it comes to the L1 instruction memory, it is also a 16 KB memory, 4-way set associative with line or block size of 32 bytes. The L2 memory is much larger, 128 KB to 2 MB based on the version of the Pentium processor. It is also a 4-way associative. This tells you that the set associative placement policy is much more prevalent in the processors, these days processors. Write back policy is again more prevalent as compared to the write through. Again that varies because the level 1 is write through, level 2 is usually a write back, okay, and the block size is the same as the level 1 block size. Main memory can be of up to 4 GB. Well, we will have a quick look of how the cache operates, okay, how a typical data that is being sent access memory reference generated by the processor is being met by the cache. So the CPU requests the content of the memory location, it checks in the cache for the data. If it is present, we will call it as a hit, okay, it gets it from the cache, therefore it is fast. If it is not present, the data is not present, we will call it as a miss, then it requires a reading from the main memory and it is slower, and the data that is being fetched from the main memory is usually placed in the cache for the sake of the fact that it may be again required, in which case the access would be faster. Then it is delivered to the CPU. So in order to easily check whether a given memory data is present in the cache, we may use what are called as tags, which helps in organizing the data in the cache and checking or searching in the cache, okay. So the organization between the main memory, the data in the cache, and its relation to how they are being retrieved from the main memory is shown in this slide. So the main memory, okay, let us say it has got the size of the address bus is n bits, which means it can have 2 power n locations numbered from 0 to 2 power n minus 1. What we will do is we will club some number of words together. In this case, k words are clubbed together to form what is called as a block. The reason for doing it, whenever we bring a data from the main memory to the cache, we will always bring it in terms of blocks. We will never bring it in terms of words, because if we do so and store it in the main memory, then the overhead involved in finding where a given data is present in the cache and if it is whether it is present will be too much. So searching the cache becomes difficult. So the unit of transfer between the main memory and the cache is in terms of blocks. There is also another name that is prevalent, which is called as the line, cache line. So we will use these terms cache line and cache block interchangeably. So here you have a block of k words. This is one block. You will have another block of k words. These blocks can be fetched and placed in the cache. So if a cache is brought, a block is brought, it is placed in one of the location, which we call it as the block frame. So a cache has got a number of block frames. Each block frame can hold a block. So the blocks that are brought from the main memory are loaded into an appropriate block frame. Every block frame will have a region called as the a field called as the tag. We store in the tag the relevant information that is required for knowing which block from the main memory is currently present in that block frame. So this tag is used for the purpose of searching in the cache to find whether a given block is present or not. So there will be a restriction on the number of blocks that can be present in the cache. That depends upon the cache size. So a cache may hold, let us say, C blocks. So they are numbered from 0 to C minus 1. So only up to a maximum of C blocks from the main memory can be brought and kept in the cache, and each block is of size k words as in the case of the main memory. Now we will look at some of the characteristics of the main cache memory and how it affects the performance of the main memory. So first, there are certain terminologies which will go through it. Hit. By hit we mean whenever a CPU sends address for searching in the cache, and if it is present, the corresponding data is present, we call it as an hit. Whereas a miss is one when the corresponding data is not present in the cache. Okay. So if there is a miss, then we have to go to lower levels of memory, that is from L1 we have to go to L2 and then search. If it is still not present in L2, which means an L2 miss, we have to go to L3 and so on. Then miss rate. Miss rate is the fraction of memory references that are not found in the cache. Okay. And there is also what is called as the hit rate that you can define. It is the fraction of memory references made by the processor which are present in the level 1 memory, and hit rate plus miss rate should be equal to 1 because they are all the fractions. Or there is another way of defining is the probability that a memory reference that is generated by the processor, okay, can be met by the level 1 memory is called as the hit rate of the level 1 memory, and 1 minus the hit rate is the miss rate. Okay, the typical numbers for the miss rate will be in terms of percentage it can be 3 to 10% for the level 1 memory, or in terms of fraction it is 0.1 or 0.03. It can be quite small also depending upon the size of the cache. Then the hit time. The time to deliver a line or block in the from the cache to the processor, okay, is what we call as the hit time. Again it varies from the level to level. In the case of the level 1 memory, it can be just one clock period. So in one clock period we can search, and if there is a hit we can take the data from the level 1 cache. Whereas for the level 2 cache it can be up to 8 clock periods. So these will decide the effective access time of the hierarchy structure. Then suppose if there is a miss in the level 1 cache, then we say it is a miss and we have to pay a penalty for the miss because we have to go to the higher level, that is the level 2, and then search it, and each incurs an additional time delay. We call it as the miss penalty. So the additional time required because of a miss is what is called as the miss penalty. And in terms of the clock period or clock cycles of the processor, typically we may incur 25 to 100 cycles if it were main memory. If it were the level 2 memory, it can be, as we have already seen, 8 clock periods. So a quantity that is of interest to us is the average access time. Given a memory reference that was made by the processor, on the average how much time does it take to access the data? Okay. So we can give a formula for it. Always we have to search in the level 1 memory, and the corresponding time is called as the hit time. Then if there is a miss, then only we will go to the lower levels of memory. So that happens at the rate which is called as the miss rate. At that rate we will incur an additional time which we will call it as the miss penalty. So average memory access time, AMAT, which is the usual acronym for that, is given by hit rate times miss rate into miss penalty. So here is an example of showing how the average access time has different components. So here you have got the CPU with certain registers in a register file, then a fast cache memory and a slow main memory. So suppose there is a word that is required to be stored in the register from the main memory, then we give a memory reference which goes to the cache, and then it has to be, if there is a hit, it will be fetched from the corresponding line where there is a hit. The corresponding word is retrieved and brought into the, loaded into the register. Okay. So data is in the cache a fraction of the time, which fraction h times it is present. Okay. If h is equal to 98% or 0.98, so then 98% of the time the actual access time is nothing but the time to access the fast cache, which is CFast. If not, we have to go to the main memory and then fetch it from the main memory and load it into the cache in one of the lines of the cache, and then forward it to the register. So we will go to the main memory 1 minus h fraction of the time. If it is 2%, 2% of the time we will go to the main memory and incur an additional delay which is C slow. So we can write the effective access time C effective as h into C fast. The h is the fraction of the time the access is met by the cache itself, which incurs a delay of just C fast. If there is a delay, if there is a miss which occurs at a rate of 1 minus h, then the penalty is C slow plus C fast, because anyhow we have to search in the cache which takes a time of C fast, and because of the miss we will go to the slower main memory and incur an additional delay of C slow. So this is the overall time that it takes. We can club the factor having C fast together. Then if you take a common factor C fast, we will have h plus 1 minus h, which is equal to just 1. So we can rewrite it in this manner, or in other way, this is a constant delay we will always incur, because at least we have to search in the cache in order to take the item. So if there is a miss, then only we will go to the main memory and incur an additional delay of C fast. Okay. Then there is another way. So we have looked at it in terms of the delay, that average memory access time. We can also find out what will be the effect of cache miss on the number of cycles it takes to execute an instruction. So here is an example. For example, we have a level 1 system having a level 1 and level 2. Okay. Then this is usually a RISC processor, which is a pipelined processor. In the ideal case, it will take 1 cycle to execute an instruction, but because of various hazards present in the RISC processors, it may take more than 1 cycle. Let us assume it takes 1.2 cycles per instruction. So CPI indicates cycles per instructions, which is 1.2. This is the best case that will occur when there is no cache miss. If there is a cache miss, it will incur additional delay. Let us assume that there is on the average 1.1 memory accesses being made by every instruction, because you may use an load or store instruction which involves memory references, or you may use fetch an operand using one of the addressing mode like indirect addressing mode and so on. So a memory access may be required. So this is what it is. So what we are interested is in finding the effective cycles per instruction, taking the cache miss into factor. The first thing is, let us say the level 1 has got an local hit rate of 95% and the level 2 has got a local hit rate of 80%. What we mean by local hit rate is that the fraction of references that are made to that level, okay, which are really being satisfied, is what we call as the local hit rate. That is the number of references to that level divided by number of references that are satisfied by the level divided by the total number of references to that level. So 95% of the time a memory access to level 1 can be satisfied, and 80% is the local hit rate of the level 2, which means 80% of the references that go to level 2 are satisfied by the level 2. Here again it can be seen that only 5% of the time we go to level 2. Out of those references, 80% are satisfied by the level 2, which means we will have 80% of 5% is the percentage of references generated by the CPU which are satisfied by the level 2. So 20% of 5%, which is 1%, actually reaches the main memory and fetch from the main memory. Okay. So how much is the cycles per second? First we will look at the effective access time. So the C effective, which is the effective access time, as we have already seen, is the access time of this fast level or the level 1 cache. Whenever there is a miss in the level 1, which is 1 minus h1 is the miss in the level 1, we will incur a delay of C medium, which is this one. C medium is the access time of the level 2 one. If again there is a miss in level 2, which is 1 minus H2, we will go and access the slower main memory, which incurs a penalty of C slow. So this is the total time it takes effective memory access time. In terms of the cycles per second, okay, the total average cycles per second is, there is a minimum of 1.2 cycles per second every instruction takes because of the nature of the processor, which is a pipelined one, and in addition, for every memory reference that is being generated, we will incur more delay. On the average, there is a 1.1 memory references being generated, and if whenever there is a miss, so it takes only one cycle to fetch it from the level 1 memory. So it will be just 1.1 if there is a hit in the level 1 memory. If there is a miss which occurs at a rate of 0.05, we will incur a delay of 8 cycles, that is what this 8 is. And if there is a further miss in level 2, which will be 1 minus 0.8, okay, then we will incur an additional delay of 60 cycles. So putting it all together, we will have 2.3 cycles per instruction is the effective access time, the total effective number of cycles that takes to execute an instruction. Well, now we will look at the various metrics of the cache. First is the cache size, which is specified in terms of bytes or words. So it's obvious that the larger the cache, the more the data it can hold, but because it is larger, it is also likely to be slower. Then the block size, that is the unit of transfer between the main memory and the cache, is what we call as the block or the line. Its size plays a role. The larger the size of the cache line or block, the more the data we can fetch it from the main memory at one go and load it into the cache, okay, whenever there is a cache miss. It can improve the hit rate because we are bringing more data, and as we will see later, it will improve the locality, spatial locality, but we may also end up bringing low utility data, that is it will occupy more space in the cache, thereby it will reduce the amount of space that is available for other data which is to be brought. Another factor that plays a role in the access time of a cache is the placement policy. Where do you place the data in the cache which is being brought from the main memory? So we call this as the placement policy or the cache organization scheme, because how do you organize the data in the cache is closely related to the placement policy. We will see that there are 3 placement policies: direct, fully associative and set associative. It has an implication on the speed with which we can access the data and also on the miss rate. Then the replacement policy tells whenever there is a need to remove a block in order to make room for a new block, which block would you choose for replacement. So it will also have an impact on the misses, future misses. Then the write policy, okay, whenever the processor writes data into the cache, okay, then how do you handle it? Whether you will write only to the cache or you will also write it to the main memory. Based on that, we have got 2 schemes. One is called the write through, another is called as the write back, and these will have implication on 2 things. One, the time incurred in fetching a data from the cache, and also a problem called as the cache coherence. We will look into these in details in the following slides. First, cache works on what is called as the locality of reference. The principle of locality is the one which is the main motivation for going in for the cache memory. There are 3 localities that can be thought of. These are being defined based on the generic characteristics of a typical program. What can normally be found is a typical program, whenever it runs and generates memory references, These memory references will not be randomly distributed in the address space of the processor. You can predict what would be the pattern in which the memory references would be done. Okay, and this locality of references basically captures these characteristics. The first is what is called as the spatial locality. What it tells is references tend to be localized in the address space. That is, if an address is being referenced, okay, there is a tendency for references close to that address to be referred in the future again and again is more. This follows from the modular nature of the programs and structures like loop and data structures like array. Because if you have a loop being executed certain number of times, say 256 times, then you would see that the body of the loop will be fetched again and again. Then we will see there is a spatial locality. Similarly, an array in which the elements are stored in successive memory locations, their references will also be localized. A more specialized spatial locality is what we call as the sequential locality, which tells that the next reference is likely to be the address which is next to the previous address that is being referred. So this is obvious, it follows from the way the control flows in the program. That is, usually we will fetch instructions one after another which are in successive addresses and execute it. So there is a sequential locality being executed by it, or whenever you refer elements one after another in an array and process it, then sequential locality is exhibited. Then you will have the temporal locality, which tells that there is a tendency for locations or addressed which are to be referred, which have been referenced in the recent past. Okay, that is, references are clustered in the time axis. If you refer a particular item, you may again access it in the future again and again for some time before going to a different locality in the address space. So loops, temporary variables, stacks are examples of which exhibit the locality of reference, because you use a temporary variable to store a partial result which is again used for the further computation. For example, here you can see a structure, a loop structure, where you access elements A and B, okay, in sequence, exhibiting strongly the sequential locality and the spatial locality. With that, we can define what is called as the working set. A working set is a subset in the address space which is most likely to be referenced by the program at any given time. That is the very simple definition of a working set. So we can define, we can come up with a subset in the address space called as the working set at any given time, and it is a function of various quantities. One, I, the level in which you define the working set, because the working set of the level 1 cache memory will be something different from the level 2 cache memory. Okay. Then the time at which you define the working set will also define what the content of the working set will be. As time progresses, the working set also will change, because you will be executing a particular procedure at one given time, and the working set will be concentrated in that in the memory where this routine is being stored. When we go and then execute some other routine, the working set will totally shift to that address locality. So it is a function of time. Then the window of time over which you want to find the working set will also define the content and the size of the working set. Suppose you want to predict the subset of the address space which is likely to be referred by the program from the given time t to t plus 100 millisecond, then the time window is 100 millisecond. So that will decide the size of the working set. If you want to predict it for a larger window size, for 200 millisecond, naturally you should have a larger content of the working set. Then the size of the working set, if you put a restriction on the size of the working set, it will have an impact on the time, the window over which you can predict, or the amount of the hit within the working set that you can get. Finally, there is a hit rate. For a given working set, we can define a hit rate of what is the probability that the next access will fall within the working set. For example, if you fix the size t, delta t and I and all these things, the hit rate may be fixed at a given value. Or if you want the hit rate to be some other value, let us say 0.95, then accordingly the size will change. Okay. So if the hit rate is more, you should have naturally a larger size to define the working set. So the idea is you identify the working set for each level and use efficient memory management technique to bring those working set into the appropriate level and load it. So the working set of level 1 cache memory is loaded into the level 1 cache memory and so on, so that the higher hit rate can be achieved. Now we will talk about the various placement policies of cache. Okay. So there are basically 3 cache placement policies or cache organization schemes. They are the direct mapped, fully associative cache placement policy and the set associative cache placement policy. So in the fully associative cache placement policies, it is the most flexible method. A block from the main memory can be placed anywhere in the cache. There is no restriction. Okay. So it is very fast to search because it is very flexible, but it is a costly memory, as we will see. Then in order to make the search in the cache memory efficient, easier, we can use a scheme called as the direct mapped cache, where every block in the main memory is mapped onto a given block frame in the cache. Okay. So that is called as the direct mapped cache. So each block has got only one place or one cache frame in which it can be placed. It puts a large restriction on where a cache block can be placed. However, because of this restriction, search becomes very simple. We have to only look into that particular place in order to find whether the item is present or not. Usually we will use a scheme called as the mod function in order to find the mapping of given a block address in which block frame it gets mapped onto. That is, if block address gives the block number of a main memory block, you divide it by the number of blocks in the cache, okay, and take the remainder, and that would give you the block frame number in the cache where it is to be placed. So that is the scheme the direct mapping uses. Now you have the set associative cache, where you group a number of block frames into set and every block is mapped onto a set. So whenever we fetch a block from the main memory, it has to go only to that set, but it can be loaded in any one of the block frame within that set. So that is called as the set associative cache. So again, how do we do the mapping? You take the block number of the block in the cache, divided by the number of sets, you would get a remainder, and that remainder will tell you the set number to which it has to be mapped. Okay. So again, we will look at these schemes in detail in the coming slides. So as we will see that this is the most practical scheme that is prevalent in the cache memory design. So in terms of a diagram, we will see, given a block in the main memory, okay, like this one, a block in the main memory. So where can it go if it is a fully associative, or if it is a direct map, or it is a set associative? So here in the main memory, this is the main memory, okay, you have got 32 sets, 0 to 31 sets, blocks are there. Okay, let us look at a block number 12. Okay, what are the potential block frames to which it gets mapped onto under different block in different cache organization schemes? Okay, in the case of the fully associative scheme, this block 12 can be placed in any one of the block frames. there are 8 block frames, 0 to 7 is the numbering that we have used for those 8 block frames in the cache. Okay, this block can go to any one of the block frame in the cache memory. Whereas in the case of the direct mapped scheme, then this block is mapped onto a given block frame. It can only be resident in that place. It cannot go into any other block. It can only go to this particular block. How do we generally find it? You take this block number, that is 12, and then divide it by the total number of block frames in this cache, which is 8, and you get the remainder. Okay, the remainder of that is 4, and that is the place where it is mapped onto. Now coming to the set associative scheme, you club 2 blocks to form a given set. So there are basically 4 sets. Okay, 4 into 2, that is totally 8 block frames, but 2 block frames per set, so 4 sets. Every block is mapped onto a given set. So the mapping function now will tell that the block number, that is 12, is divided by the set number, which is 4, to get the remainder, which is actually 0. So it is the 0th set to which it can go. There are 2 block frames in that set 0. You can place it in any one of them. That freedom is being given. So this is in nutshell the way the 3 schemes work. We will look at it in detail in the following slide. Okay. In general, how a block is being searched in a cache is as follows. The processor generates an address, okay, which has 2 parts. One is the block number in which the address falls, and another is location of the word within the block, because a certain number of words are clubbed together to form a block. It may be 8 words per block or 16 words per block. So based on that, you have to give the word position of a word within a block. So this block offset basically is a group of bits which will tell the position of a word within the block. We will call it as the block offset field. Then the block address. So this is the block of the main memory which you are looking for. In order to look for that in the cache, what we will do is we will look for the set or the block to which it gets mapped onto. So for that we will do a mod operation by dividing by the number of sets or the number of blocks and take the remainder. So if you do that operation, normally it is the lower order bits of this block number which will come out of the remainder. For example, if you take this block number and then divide it by 8, then the lower order 3 bits 0, 1, 2 will be the one which will come out of the remainder. So by directly looking at these lower order bits of this block number field, you can find the set or the block to which it gets mapped onto. So we call this as the index. So this is being used directly to go to that block or set. Then what can change is the higher order bits which will tell the actual block that gets mapped onto that set. So that we will call it as the tag. So we have to again search, check whether this tag of the block which you are looking for matches with the tag of that particular field. Okay. So we will again look at it in detail in the coming slide. We will first start off with the fully associative mapping. So in this scheme, let us take an example wherein we have got a block of size 16 words, which means you need 4 bits to specify the position of the word within the block. So these 4 bits of this address, this is the main memory address, will give you the word offset field, okay, and the upper 12 bits will give you the block number. See, the main memory is of size 64 words, so each block is of size 16 words, so there are 4K blocks and these blocks are numbered from 0 to 4095. So there are 4K blocks, therefore we need a 12-bit address to specify the block number. So that is what the processor generates. Now what we have to do? We have to first check whether this block is present in the cache. Now this is a fully associative scheme. So how the blocks are being brought and loaded into the cache? Each block that is being brought can be loaded in any one of the block frame. For example, the block 1 can be present in the 5th block frame. The block I can be present in the 0th block frame. So anywhere you can place it. So having placed a given block in a given block frame, you should remember it, and for that you should store the block number in this field called as the tag. So the tag field basically tells what block is currently residing in that block frame. So different block frames are now loaded with different blocks from the cache. Okay, so let us say the cache has got a total capacity of storing 128 block frames. So they are numbered from 0 to 127. So a given block can be resident in any one of the block frames. So there are potentially 128 block frames which can hold this block. So we have to do a comparison. So what we will do is we will compare this tag with all these 128 tags simultaneously using 128 comparators. If there is a match, we will call it as the hit. Then the corresponding block is used to retrieve the word from that block. Okay. So because you need more comparator, the searching is expensive. Well, in little bit more detail, so you have got a main memory address which is of size S plus W. W is the word offset, S is the specifies the block number. Okay. So in this fully associative scheme, there are different blocks. Each block in this case stores 4 words. So this block can be brought and loaded into this block frame. This block can be brought and loaded into this block frame. So this is how blocks are being populated. So given a particular memory address, this tag field is compared with all these tag fields of all the block frames. So there is a simultaneous comparison that goes on in this comparator. If there is an hit, okay, if there is an hit on a particular block frame, then this word offset is being used to retrieve that corresponding word from this block and give it to the processor. In case there is a miss, then we take that field S, okay, and then club it along with the W, that is the word offset, and fetch it from the main memory, okay, and it may be loaded into the cache. So in summary, the address as S width of S plus W, this is the word offset, this is the block number. The number of addressable units is 2 power S plus W. This is the memory address size of the processor. The size of the block is 2 power W because 2 power W words can be stored in the block. The number of blocks in the main memory is total memory capacity divided by the size of the block, which is just 2 power S. 2 power S blocks in the main memory. So we need a block number field is of size S bits. The number of lines in the cache or blocks in the cache can be found out by dividing the cache size divided by the block size. So this many block frames are there in the cache, and the tag size is equal to the size of the block number field, which is S in the case of fully associative mapping. Coming to the next scheme called as the direct mapping, the main advantage is that it is simple, it is inexpensive because you don't need so many comparators. Okay, we put a restriction on where a block can be loaded into the cache. Because of this restriction, you don't need to search the entire cache for a block. You just go to that block frame to which the block is mapped onto and only check whether it is present or not. So here what we do, again the same example, we have got blocks of size 16 words, so the word offset is 4. There are 4K blocks in the cache, in the main memory. So it's a 12-bit field, this is 12-bit. Then what we will do is, every block is loaded onto a block frame. The mapping function is nothing but block number mod 128. So a block number n, okay, n mod 128 will just give you a 7-bit number, okay, a 7-bit number which will be the block frame number to which this block is mapped onto. You can see that a 0 will be mapped onto 0, 1 will be mapped onto 1 and so on, and 128 will again get mapped onto 0 and so on. So this 7-bit number is being used to identify the block frame to which this block is mapped onto. Just go there, but because there are multiple blocks which will get mapped onto a given block frame, out of which only one can reside, we cannot be sure that this given block is present in that block frame. So for that we use this tag field, okay. In fact, there will be 32 blocks in this main memory which will all get mapped onto a given block frame. So this tag field, 5-bit tag field, will specify which among that 32 blocks, okay, which are all mapped onto a given block frame are currently resident. So you have to check whether there is a match between this tag and this tag, and if there is a match, there is a hit, otherwise there is a miss. Only one comparison is needed, therefore it is faster, but it puts a lot of restriction, because if there are two blocks, okay, say 0 and 128, which are repeatedly requested, both being mapped onto a block frame 0, if one is being brought, okay, and if there is a requirement for 128, then we have to replace it. So there will be a frequent misses which will be encountered. So in the case of direct map cache organization, the S plus W is the width of the address bus. So it has 3 parts: the word offset field W, the block number or the line number field, okay, and the tag number, okay. So this line number is being used to identify the block frame to which this block is mapped onto. Then the tag in that is being brought and compared with this tag. Just one comparison: if there is an hit, then this word offset is being used to retrieve the word from this block. If there is a miss, then you just go to the main memory and fetch the corresponding word, forward it to the processor, while the entire block is being loaded into a cache. So this example tells how we find the width of the tag and so on. So if, for example, if the size of the word is 16 bytes, then log 16 to base 2, that is 4 bits are required for the offset field. That is what we will fix, okay. If the cache has got 4096 block frames, then log 4096 to base 2, that is 12-bit field, will give you the block is the index field. The remaining number of bits will give you the tag. This will be the tag, okay. Here is an example of how the direct mapped cache will behave. Let us say we have an address, say a trace of 1765 are all being brought. So we will see that initially there will be a miss. Let us say there is a 1 is being referenced, there is a miss. So the entire 4 words which fall in that 0th block has to be fetched. So if you fetch it and then load it in this block, then you will have another reference 7, okay, which will fall in the 2nd block. So you will fetch it and put it in the 2nd block. The entire block with all these 4 words are being loaded in this one. Then 6 will be an hit, 5 will be an hit, okay, and then 32 will be a miss because 32 will get mapped onto the first set which was originally occupying this one. So you will load this 4 blocks, okay, into this one 32, 33, all these things, and then again 33 will also be a hit because it is already there. Then 2, again we have to bring, there will be a miss and we have to again load it into this one. So here we will see that because there is a competition between the block 0 and block 32, there is a repeated miss that is occurring. In summary, a direct mapping has got a width of S plus W. W is the word offset width. There are total size is 2 power S plus W, whereas the number of blocks is 2 power S. The number of cache lines, if it is M, which is equal to 2 power R, then there will be the width of the tag will be S minus R, and R middle bits will give you the index field which is used to identify the block number. In the case of set associative, then we club certain block frames to form a set. Let us assume that we club 2 blocks to form one set. So there are 128 sets, 128 blocks, 2 blocks per set. So we have effectively there are 64 blocks numbered from 0 to 63. So how is the placement policy working? Every block is mapped onto a set which is obtained by dividing this block number field, which is a 12-bit field, by 64. So that will give you a reminder which is nothing but the lower order 6 bits. So this 6 bits will give you directly the set to which this block gets mapped onto. So you use this 6-bit field to identify the set to which a given block is mapped onto, but it can be loaded into any one of the block frames within this set. So what we do is we use this tag field, which is the higher order 6-bit field, to identify whether the block you are looking for is present. Now you will see that there are 64 possible blocks which can be mapped onto a given set, out of which only 2 can be resident. So you use the tag to identify that. Again, coming in terms of this diagram, so you will have a address of width S plus D plus W. So this D will give you the set number, okay. You just directly go to this set. Here you will see that, let us say there are 3 blocks per set, these 3 blocks per set. So this tag is compared with the tags present in these 3 block frames. So you need 3 comparisons being done. If there is a miss, you have to go to the main memory and then bring it into the cache. If there is a hit, then you identify the word within that block using this W field and fetch it from the block frame. Again, we have got an address of with S plus W. 2 power W is the size of the block. 2 power S is the number of blocks in the main memory. If there are K blocks or K lines in the cache, then you will have 2 power K lines or blocks in the cache. Then the number of the width of it will be will be accordingly decided. There are V blocks in the cache. Then if D middle order bits will identify the block number, there will be 2 power D sets in the cache. So the number of cache blocks will be the size of the set, that is the number of blocks in the set into the number of sets, which is K into 2 power D. The size of the tag will be given by S minus D. Okay. So again, this is an example of finding the size of the different width. Okay. So if there are 16 bytes per block, naturally there will be a 4 byte offset field for the word offset. if the number of if there are 4096 blocks in the cache, if 2 blocks are clubbed to form a set, okay, there will be only 2048 sets in the main memory. So log 2048 to base 2 will give you a 11 bit field, and that will give you the set index field, which can be used to identify the set. The remaining higher order lines, which will be 17 bit, will be the tag field. So basically we have looked at the different organization schemes that are prevalent in the cache memory, okay, the various misses that can take place in the cache and how do we reduce it. If you have any questions, you can post it. So there are basically 3 questions. The first question tells what is the how about the direct mapping. The direct mapping organization tells how the block has to be placed or organized in the, how the blocks are organized in the cache. Its behavior is that because of the restriction that it puts, there may be many misses that will take place, because if blocks all getting mapped onto a given block frame compete for a space within the cache, then there will be misses. This is the disadvantage of the cache. Then the 2 more questions which are very related to each other, they all tell which is more prevalent cache organization scheme that is being used. The set associative cache placement policy or organization scheme is the most prevalent one. So most of the cache are 2-way or 4-way set associative. So that is the most prevalent schemes, which is an hybrid scheme between the fully associative and the direct map scheme. Now we will look at the different misses that can occur in the cache. So there are, we can categorize them into the 4 categories. One is the compulsory misses, okay, then capacity miss, conflict miss, and then the coherence miss. Compulsory miss, that is the first access that is being made by the program, will definitely miss because it would not have been brought earlier into the cache. So there is a compulsorily it will miss, okay, into this one, because cache is used to store some of the recently referred item. First time if an item is referred, it would not be present, therefore it is a miss called as the compulsory miss. Capacity miss comes because of the finite capacity of the cache. If the working set is larger, but if the cache size is small, you can't fit all the requirements of a program within the cache, so there will be a miss because of the capacity. Conflict miss occurs due to the placement policies, like in the direct memory access, okay. If 2 or more blocks compete for a given block frame and they are repeatedly requested, then because of the conflict in their placement, this miss occurs. It has been found that 30 to 40% of the misses are due to the conflict. Then coherence miss. If there are in a multiprocessor environment where there are more than one cores, each having its own local cache, and 2 copies of the same data is present in their local cache, if one core modifies the cache content, the corresponding data in the other cache should be invalidated, because you cannot having the same data having 2 different values. So that is called as the coherence problem, and because of that certain misses can occur. They are called as the coherence miss. So in general, the number of misses per instruction can be written as follows. Misses is given by the rate at which misses occurs, okay, into the number of memory accesses that are being done. So out of the total number of memory accesses that are being done, if you multiply it by the rate at which misses occurs, that will give you the total number of misses. So we can now combine it as follows: miss rate into the number of memory accesses per instruction. So this is one way of writing the number of misses that will happen per instruction. So this formula is something which you have already seen. The average memory access time is given by hit times plus miss rate into miss penalty. These 4 or the coherence miss is a different one. This basically these three cache misses, conflict, capacity and compulsory, can be understood by looking at the how they miss occur as against the cache size and the associativity. So this diagram figure shows the miss rate that is present in this one against the cache size. So the cache size is changed as 1 kb, 2 kb, 4 kb and so on, and the associativity is also changed from one way, two way and so on. As you would see that, so there is a finite amount of small amount of misses that are present here, which is very small. It's due to the compulsory miss. That occurs because with the first time we are bringing this item and they are not present in the cache. It is also called as the cold start cache misses. Then misses due to the capacity problem or the capacity misses are shown green in color. So this much amount of cache misses are due to the finite capacity of it, beyond which cache misses occur because of conflicts, which can be reduced by changing the associativity. You can see that if it is a one way cache, it has a large amount of cache misses, okay, whereas the two way reduces the cache miss from this line to this line. A four way further reduces from this red to yellow, the 8 way reduces it further, but you can see that beyond a point, if you increase the associativity, you will get diminishing returns. So there is an optimal value of associativity up to which you can reduce in order to reduce the conflict miss. So the three misses are compulsory, capacity and conflict. Going into that, compulsory misses, first reference to an address results in a miss. Subsequent references should not result in a miss, okay, unless there is a miss due to other factors. Dominates when the locality is poor, okay. Then we have the capacity miss. Cache is too small to hold the full working set, therefore this miss occurs. Defined as the miss that would not occur even if the fully associative cache with optimal placement of the same capacity. So if you use a fully associative cache where there is no conflict miss, and if you use a good replacement policy, which we will later on see as the optimal replacement policies, then there won't be any conflict miss, everything will be only a capacity miss. Then conflict miss occurs, okay, is neither because of these two reasons, that occurs basically because of the associativity, finite associativity. How do you reduce the miss? Compulsory miss can be reduced only by the help of prefetching. If you can predict what would be required by the cache before the process generates those references, you prefetch it and keep it ready. That is what you can do. Beyond that you cannot help, because the first encountered reference has to be a miss. Then conflict miss can be reduced by having more associativity, better replacement policies, okay. You can also achieve it using schemes other than increasing the associativity. We will see all those things. One is by using the victim cache or by using some software techniques. Capacity, you will use the cache space efficiently, keep blocks that will be referred, okay. So critical or repetitive data has to be kept, okay, and you can also use some software management techniques, divide the program into different phases of execution and allocate cache and keep the working set of all those phases within the cache. Coming to the cache performance, you can in general write the CPU time that is consumed, okay, is the time taken will be the number of instructions that is executed into cycles per instruction, okay, into the memory accesses per instruction, into the miss rate into miss penalty times the clock period, okay. So whereas the miss per instruction is given by the memory access that are generated per instruction into the rate at which misses occurs. by using this equation, we can look at what are the ways in which cache performance can be improved by reducing the miss rate. So, there are the following things can be done to improve the performance: reduce the miss rate or reduce the miss penalty. If the miss occurs, the time taken to fetch the data can be reduced, or improve the time it takes to fetch an item even in case there is a hit in the first level cache. Okay. So, we have written the total CPU time is number of instructions into cycles per instructions into the memory access per instruction. How many memory accesses are being done per instruction? For each one of them, whenever there is a miss rate, you will incur the miss penalty. So, these are the two factors into the clock cycle. So, now we will concentrate on this factor. If you reduce this miss rate, then the CPU time will be reduced. So, how can that be done? So, we will see that we already looked at the 3 C's for the cache misses: compulsory, capacitive and conflict misses. So, reducing miss can be reduced by having larger block size. So, it will improve the spatial locality and reduce the cache misses, or having higher associativity, or using the concept called victim cache, or we can prefetch the data to reduce the compulsory misses. It can be done for both instruction as well as data, and two techniques can be used: hardware prefetching or software prefetching. Then we can also use some optimization techniques at the compiler end. First, this diagram shows how larger blocks can help, but there is an optimal size of the block. So, here the miss rate is being shown against the block size. So, block size is changed from 16 to 256, and here the red line shows that it is a 1 KB cache. 256 shows that it is a 256 KB cache. First thing we will notice it, as the size of the cache increases, the miss rate decreases, because if you have 256 KB cache, okay, because of its larger capacity misses reduces. As compared to 1 KB cache, 2 KB cache has got reduced miss rate. From 15% we have got to about 8%. Within the given cache size of say the 4 KB, then as the block size is changed from 16, 32, 64 and so on, from 16 to 32 the miss rate decreases, again it decreases to 64, but then it increases. So, we will see that 64 is an optimal value of the block size for the 4K sized cache. So, this tells that the larger block improves, but there is an optimal block size. Then victim cache is a technique wherein the blocks that are being replaced at one level of the memory, cache memory, are being stored in the victim cache, so that in case if it is required again, we do not incur a miss, we can feed it to the processor. Okay. So, you add a buffer to a place for storing the data discarded by the cache. Victim cache is a small but usually a fully associative but not necessarily cache that holds few of the most recently replaced blocks. So, blocks that are replaced are victims of the cache replacement techniques, and this is a cache that holds these victims. So, it is called as the victim cache. Okay. So, there is a study which tells that, so a 4 entry cache victim cache can reduce up to 20 to 95 conflict misses. Okay. For example, this processor uses victim cache. The next is hardware, the prefetching. So, you can prefetch instructions and then store it. That way we can reduce the number of misses. So, instructions can be fetched from the instruction L1 memory, cache memory, and put it into the instruction queue. Okay. so that those misses can be reduced. Okay. So sequentially you can prefetch instructions from the instruction memory and put it in the instruction queue, and there is also a possibility of branches occurring, in which case you can do a branch prediction and the predicted sequence can be brought and loaded into the instruction queue. Coming to the data would be more difficult to prefetch because generally instruction follows strictly the sequential locality of reference, so prefetching will be much easier, whereas data may not exhibit a good locality of reference, so it is difficult to predict. Okay. So in which case these two questions become relevant: what to prefetch and when to prefetch. So here, how to know which data has to be used? Unnecessary prefetch will populate the cache will waste the memory and will populate the cache, which results in what is called as the cache pollution problem. That is, you prefetch and bring something into the cache which was not actually required. You have, as a result, you have replaced some of the possibly more useful data. That is called as the cache pollution problem. Then when to prefetch is another thing. You should try to prefetch when the cache and the main memory bus is free, so that prefetching itself should not reduce the time incurred by the actual references which are needed. Okay. So whenever there is the bus happens to be free, you can make use of it to prefetch it. So software prefetching, because the program knows a particular content would be required, you can insert instructions wherein fetching can be already, you can bring it into the cache and keep it before its usage. So explicit instruction can be used to prefetch the data and put it. Okay, and there are specific instruction in certain processor for prefetching into this prefetching. Compiler can also do some analysis and insert those instructions. Hardware prefetching can also be done in certain applications. Then writing data into the cache, okay, can be improved using a technique called as the write buffer. Okay, so what we basically do is, when we write certain values into the main memory, it incurs time. So we store it first into what are called as the write buffers and then load it or write into the cache memories later. So this reduces the miss penalty. So, but when you read a particular data, it may be present in the write buffer because it is not yet written into the main memory. So you have to check the write buffer contents before a read. Okay, if there is no conflict, then the memory access is being continued. Then there is another scheme called as the write back. Okay, so here only we replace a block when there is it is dirty. We will look at these two policies later, and which time it will become more understandable. So we will look at it in the following slides which will follow, the write policies. There are also caches which are non-blocking caches. That is, if there is one references on which there is a cache miss, then it incurs a time in order to fetch the content from the main memory and load it into the cache. Then what do you do with other instruction? Should you stall it or can you allow it to continue? So whenever you have an out of order execution CPU, you can allow a following instruction to make other memory references. So those are called as the non-blocking cache. A given memory reference does not block, a miss does not block the subsequent memory references. Okay, so it can significantly increase the complexity of the cache controller because there can be multiple outstanding memory accesses with misses. Okay, but if we have multiple memory banks, memory bandwidth can be improved and we can satisfy multiple simultaneous memory references. Pentium Pro for example have up to 4 outstanding misses. Then you can have a second level cache which can be used to reduce the miss penalty, because instead of going to the main memory and fetching it, which takes more time, for example 60 nanosecond may be the time a main memory incurs for every memory references. If you introduce a second level cache which takes 8 clock periods instead of 1 clock period, then the miss penalty can be reduced. So L2 cache can be included. What will be the average access time? If you have an L1 memory, the hit time for the L1 memory plus the miss rate of the L1 memory into the miss penalty. If you include the L2 cache, the miss penalty of L1 can in turn be written as follows: hit time for L2, and whenever there is a miss in L2 which occurs at a miss rate, miss penalty of L2 can be the penalty you incur. Clubbing both these equations together, we can write the average memory access time as hit time of L1 plus miss rate of L1 into, for this equation you replace this entire thing, hit time of L2 plus miss rate of L2 into miss penalty of L2. So this is how you reduce it. So then we have already looked at the local distinguish between the local miss rate, which is the fraction of memory references coming to that level which are missed, whereas the global miss rate is the fraction of references coming from the processor which are missed by a given level, okay, which for the global miss rate of L2 can be found out as the local miss rate of L1 into the local miss rate of L2. Then coming to the conflict misses, it occurs basically because of the restriction in the placement. The problem is severe for the direct mapped, okay. So in the case of set associativity it is lesser, and you can use set associative with larger associativity. Victim cache can also be done. So that gives you an overview of how different cache misses can be categorized and how it can be reduced using different techniques. We will move on to the next cache management policy, namely the replacement algorithms. That is, whenever there is a cache miss, you will fetch the block from the main memory and feed the data to the processor. The copy of that block can be loaded into the cache, because if that block is again required in the future because of the following the temporal locality of references, it will be present in the cache and it will reduce the future cache misses. So if you do so, necessarily if all blocks are being occupied already, you have to necessarily replace an existing block in order to make room for a new block. Then we have to kick in one of the replacement algorithms. So there is no choice in those cases, or there may be, due to conflict reasons, there may be only few possible block frames where a given block can be kept. Because of that, a replacement needs to be done. These are the popular replacement policies. Least replacement recently used are LRU schemes, the FIFO or first in first out scheme, least frequently used, and random replacement. Also pseudo LRU is also another scheme that can be popular. So replacement algorithm, the first is what we call as the optimal algorithm. We will see how it works. Then the random replacement algorithm, LRU, round robin or the first in first out replacement algorithm, pseudo LRU, which is an approximate LRU algorithm which is easier to implement. First we will talk about the optimal replacement. What this policy tells is, given a sequence of memory references, if you have to replace an existing block in the cache, replace that block which will not be required in the near future. Out of all blocks which are going to be referred in the future, the one that is going to be referred, okay, in the distant future is the one which can be removed. This can be employed only if you know the future references that are going to be done. Let us assume for a while that the entire reference string or references are known. Okay. So here we have a cache with 3 blocks. We have shown against the memory references being made how the content of the cache changes, okay, and how the caches or blocks are being replaced. Okay. So first block 1 is being referred, it is put in the cache, then 2, then it is also put, but it is arranged in such a manner that the most recently here you place it in 2, and then the cache 1 block 1 is placed, then the 3 is referred, you can place 3 here, 2 1. So there are 3 blocks are being present. Then the 4th block is being referred and it is not present in 3 already in the cache because 3 2 1 are present in the block. Which one among these 3 has to be replaced when the 4th is to be brought? Now look at the reference, future reference, and find out which block is not required, okay, in the near future among 3 2 1. So you would see that 1 and 2 are required immediately. So if you replace 1 or 2, there will be a misses soon, but 3 is not referred, okay, for quite some time, only here. So you replace 3. So 3 is replaced and then 4 is brought in. After that 1 is referred, it is an hit, 2 is referred, it is an hit, then 5 is referred. Again we need to have a replacement scheme. Just look at among what is being present, which can be replaced. Again 1 and 2 are required, so 4 is not immediately required, so replace 4 by 5. So again 1, 2, 5 are referred, there are 3 hits followed by 3 and so on. So this is how the optimal policy will work, and you can say that this is the best policy that one can think of because it reduces the misses. But the problem with this policy is that you do not have the future references with you when you take this implement these schemes. So this scheme is an idealistic policy which cannot be implemented in practice. It can be used only as a benchmark or a gauging technique for comparing the performance of realistic replacement policies with these optimal policies. So it is theoretically best one, okay, but produces the lowest possible for replacement, impossible to implement because future knowledge is required. So it is used to gauge the performance of other algorithms. Now we will now coming into possible realistic replacement policies. Simplest is the first in first out or the largest resident time algorithm. That is, when you want to replace a block, among those blocks which are present, the one that has come first, okay, or in the oldest one is the one which has to be replaced. So the same example with the same reference string. So block 1 is referred, it is being placed here, block 2 it is placed, block 3 it is being placed, then block 4 is being referred, and it is a miss because 3 to 1 do not is what is present in the cache, 4 is not present. So which one would you replace? You replace 1 because among 3 to 1, 1 is the oldest one, it has been brought first. So you replace 1 and bring 4. Then again 1 is required. So you have to replace 2 which is now older, the oldest among 2, 3 and 4. So 1, 4, 3 will be there. So what we see is that the oldest one does not, 1 has been replaced because it was oldest, but that does not necessarily mean that 1 is not required in the future. Here 1 is again was needed, but it has been replaced. So this is how it goes. So 2 when it is required, okay, you replace 3, and when 5 is required you replace 4, and these are hits. When 3 is required you replace 2 and so on. So FIFO is a simplest page replacement algorithm. The problem that is, okay, the number of faults can increase if you are not if a given page or a given block is referred very frequently. We have a scheme called the LRU, which is the most popular scheme, okay, What it basically uses the temporal locality of references. It looks at the past references and then finds uses the temporal locality. At the time of replacement, it looks at all the blocks and keeps those blocks which are being recently referred. Among those blocks which are present, the one that has been least recently used is the one which is being replaced. So what you have to do is, for that you have to arrange the blocks present in the cache in the order of the how recently they are being referred. The most recently used cache, call it as MRU, should be at one end, the least recently used cache should be at the other end, which means that after this block 2, which is the most recently used, 5 is the next most recently used, followed by 7, C0, 4 is the least recently used. So this is the candidate for replacement. So always arrange it in the form of with a measure of recent references. So now if there is an access, how do we always keep this structure of what is called as the LRU stack to decide the least recently? So suppose if 0 is being referred, it is a hit in the cache, but because it is recently referred, it has to go to this position, and therefore 2 will be less recently referred than 0, so it should occupy this position as compared to this. Then 5 will occupy a position 1 behind 2 and 7 will occupy a position 1 behind 5 and so on. So if whenever there is an hit, bring that block and put it in the MRU position, and all blocks which are in between MRU and that position are incremented by 1, moved by 1 bit position. All blocks which are in this position are not changed, their count will not change. Whenever there is a miss, the LRU block is being replaced, and then the block that is being brought is put in the MRU position. All these blocks are being shifted by 1 bit position. So this is how it happens. Okay, so there is a miss, replace the block 6, then all blocks are moved. So 3 moves here, every block is moved, and 6 comes here to the MRU positions. So this is how the LRU keeps track of the LRU stack. So this is a very good policy, okay, but the only thing is that the overhead involved in keeping this information is too much. That is why pseudo LRU policies which approximates these LRU policies are good. Then we will get into the write policies. What happens whenever there is a memory write? Okay, there are two things we can think of. One is called the write through, another is the write back. Write through policy, whenever it updates the cache, level 1 cache, it also updates all other higher level, lower level memories, level 2, level 3 and the main memory. Whereas in write back policies, only the level in which there is a hit is being updated, and because of that this corresponding copy in the main memory will not be updated, but if a block is going to be replaced, at that time the updation takes place. So you postpone updating the main memory content until the time at which the block is going to be replaced. Okay, but whenever a block is replaced in the level 1 or level 2 cache, there is no need to update the main memory, because you might have brought up a block and read it many times without even modifying it one. So you maintain a bit called as the dirty bit. This bit is being set whenever it is modified, and it is not set or it is clean when it is not modified. At the time of replacement, if the block is clean, there is no need to write back. If it is dirty, then only it is written back. So read access to the cache, okay, is done as follows. A cache sends the index to the CPU sends the index to the cache. If there is an hit, then the cache sends the data to the CPU. If there is a miss, then it goes to the fetching from the main memory. So until this time, you have to stall this instruction. In other words, what the other way of handling is that CPU inserts no op instructions so that it decodes and does not change any flow of the normal flow of the instruction is not affected by inserting no ops, and when the data arrives, the actual instructions are being executed by the CPU. Now we will see the various cache read and write algorithms, okay, one by one. Let us first see what happens when there is a hit on a read. So a CPU generates a data and a memory reference, and it is a hit, okay. It sends the index as well as stack to the cache. The data is present, therefore there is a hit, and it's for the purpose of reading. So the data is being given by the cache and it is taken by the CPU. Because it is a read operation, there is no need to worry about the write back or write through policies, because the content of the block in higher levels of memory is not being changed. It is only a read operation. So it can be just read from the CPU cache itself. What happens when there is a miss on a read? So the CPU sends an address consisting of the index and the cache tag to the cache, but it is not present in the cache. So there is a cache miss. So what we have to do? We have to go to the main memory and fetch it. So the address and data are being sent to the main memory, and the data is being brought, okay, and given to the CPU, while a copy of the data is also being forwarded to the cache, because it might be required in the future. So this may kick in a replacement policy, a cache block may be replaced and this new data can be stored. This is what happens in a read miss, okay. Then we will look at the write policies. Whenever there is a cache write, as we see, there are two things. One, there can be a write back policy, that is whenever there is an updating of the value in the cache, you only update the level 1 or level 2 cache, do not update the main memory, update it only on the time of replacement, okay, by looking into the dirty bit. The other is the write through policies. Whenever the cache is updated, the main memory is also updated. Again, there are two ways in which we can handle the misses in the case of writing. Whenever there is a write that occurs and there is a miss, so the data is not present in the cache, it is in the main memory, and you have to write into the main memory content. Now, would you bring that block into the cache? Okay, because if we are using a write through policies, whenever you write into the cache, you also write into the main memory, you don't save time. So instead of bringing into the cache, you just leave it in the main memory itself. That is called as the no write allocate. It assumes that a write is frequently going to be followed by write. There is no point in bringing that block into the cache, because write through policies incurs a full main memory access delay. Whereas if you assume that a write can also be followed by a read, then when you update the main memory on a miss, if you bring a block and load it into the cache, which is called as the write allocation, then the future cache reads would be will have lesser time. So that is the two variations of the write through policies. So here is the write back policy. So there is a reference and there is you only modify the content of the cache. If there is a hit, then the cache alone is being modified. In the case of write through, you not only modify the cache, but you also modify the main memory content. Well, now whenever you use a write through, it has the advantage that all the time the content of the cache and the main memory are the same. There is no problem with the coherency, okay. But writing into the main memory is time consuming. So should you wait, should they make the processor wait till that time, or how it can be done? You can introduce what is called as the write buffer. So you introduce a small buffer called as the write buffer, in which the content is to be written to the main memory, Okay, instead of waiting for the main memory value to be written, you store the address and the corresponding data pairs in this write buffer, so that in the background these write operation takes place while the CPU continues to work on to fetch and execute the program. Okay, so again this is very similar to what we have already seen. You can use a write buffer to write into the main memory. So the write back policy, same what we have already discussed. You don't bother to update the main memory. Okay, the cache will not be consistent with the main memory all the time, but at the time of replacement it will be consistent. So we can use the concept of dirty block while at the time of replacement. So the main memory address has got two parts. The cache index is being used to identify the block, the cached line. You check whether the block is valid, okay, and if there is an hit by looking at the match in the tag, then it is an hit. Then you retrieve the corresponding word and give it to it. Okay, and if there is a miss, only if it is dirty, then it is replaced. So on comparing, the write through policy is a very simple policy because there is no overhead involved in worrying about the cache coherence, but the logic is simple, but it may be slower because it creates more traffic on the bus. Write back uses dirty bits and uses extra logic. So generally level 1 memory uses the write through, whereas the level 2 memory can use the write back policy. Now we have the problem of cache coherence. I will quickly explain what we mean by this problem. Let us assume that there are two CPUs A and B. Okay, there is a block called X, okay, which is required by both the programs running in A and B. So the first, what happens, the content of the data X, okay, is present here. So the X is being read from the main memory, its value, let us say the value of X is 1, it is being brought into the cache of CPU A. Then B also reads the data X, its value, that is the 1, is also being brought and loaded into the cache of the core B. So now at this point, the main memory content of X, the content of both the caches with A and B are all same. We say now the data is coherent or data is consistent, because all these are 3 copies of data supposed to represent the same variable X. They should have the same value. If they do not have the same value, there is a incoherency or inconsistency. An inconsistency will come when a given core changes the local copy of this data. Suppose if A stores 0 into X, then X value will change to 0, while its value in the cache of B is 1. Okay, if it uses a write through policy, then the main memory content will also immediately change to 0. So main memory and the cache memory of A are consistent, but that of the B is not consistent. So what we have to do in general is that under this condition, you will invalidate the data X in the cache of B, so that when B fetches this value X, we should not forward 1, we have to tell it is invalid, it has to be fetched from the main memory and then it has to be loaded. This is how the cache coherence problem is solved. There are different techniques. Snooping bus is one technique. MESI, modified exclusive shared invalidate messy protocol, is another method, okay, which can be used for solving the cache coherence problem. Then there is a policy called as the inclusion policies. That is, when you arrange data in the different levels in memory hierarchy, okay, should the content of level 1, should it always be a subset of level 2, or how it can be done? Based on that, there are 3 variations of inclusive policy. One is called as the strictly inclusive policy. which tells that all the contents of level 1 is also present in L2 and all the contents of L2 will also be present in L3 and so on. So level 1 is a strict subset of L2, L2 is a subset of L3 and so on. Here how it works. Let us say level 1 and level 2 are empty, the item data X is being referred, then it will be brought loaded into level 2 as well as level 1. Then let us say Y is referred, it is brought and loaded into level 2 and level 1. So here X and Y are present in L1, it is also present in L2. Now you refer some other data, as a result X is being replaced, okay, but the corresponding block in level 2 need not be replaced because it's still a subset, okay. L2 can have values more than what is present in L1, but if it is present in L1, it should definitely be present in L2. That is again obeyed, okay. But now as a result of a replacement, if Y is replaced in L2, then what happens is then the corresponding copy in L1 has to be invalidated. Otherwise, you will have Y in L1 but not in L2. Then it is not strictly inclusive. This overhead is present in strictly inclusive policies, but there is an advantage of this one is, if you know that if it is not present in higher level caches, it will also not be present in lower level caches, so invalidating becomes easier. Then there is a method called as the exclusive policies, whereas the content of L1 and the content of L2 are mutually exclusive, that is they are disjoint. So here let us say the caches L1 and L2 are initially empty, X is referred, you bring it and load it only in L1 and you should not load it in L2 because the content are exclusive. Then Y is referred, you bring it and load it only in L1. Why in L1? Because L1 is closer to the CPU, access time will be lesser, that is why you load it in L1. Now if X is replaced, then what we do, instead of just like that replacing, you bring it and then put it in L2. So because otherwise you have to go to the main memory and fetch it, you know that X is replaced because of the capacity problem and therefore it is loaded into X. So in this way L2 acts as the victim cache, okay, and this improves the cache performance under certain conditions. Then you have got a non-inclusive, non-exclusive policies, which is neither fully inclusive, strictly inclusive, not strictly exclusive. As in the previous case, X and Y are being referred, both are being fetched and two copies are kept in L1 and L2. Now X is replaced, then you don't need to replace it in the L2. Then Y is replaced, okay, in L2, you don't need to invalidate in L1. So that is the advantage of not maintaining a strict inclusive policies for the 9 case. You can also have a cache which is separate or split. Instruction and data can be separately kept, okay. This doubles the bandwidth of the cache and therefore it is good. Or you can have a unified cache, usually level 2 is unified. So instruction and data are the same cache, you have the flexibility of placing a part of the instruction or part of the data, but because the bandwidth is a problem, you may have to use a dual ported memory or you have to fetch it at the twice the clock frequency, okay, and so on. So here, because writing is also allowed, if you have an instruction unified cache, even self modifying code can be there, okay. So L1 caches are usually split, L2 caches are usually unified. Burst mode cache is a technique wherein if you have a sequence of memory references are being made, you give a first address, then they are being latched at the address port of the cache and they are being incremented one per clock period, okay, and subsequent data are being fetched in sequence. It eliminates the need to send separate address for references in sequence. Cache write buffer is something which you have already seen. Instead of writing into the main memory, you can first write into the cache buffer and then allow the writing into the main memory in background. Now with all these cache memory management that are being discussed, at last what we will wind up the lecture by giving some of the configurations of cache memories that are prevalent in different commercial processors. This is a processor from AMD. There are three architectures popular in AMD architecture: the level 1 code and data, instruction and data memory, level 2 memory, level 3 memories are being given here. We will take just one example. This example bulldozer architecture uses a 64 KB L1 cache. It is a two-way set associative cache and each block has got 64 lines or blocks. Okay, it is shared between two cores in a similar configurations for this one. Okay, it uses the write-through policies. There is also something called as the read-through policies, wherein whenever you fetch a block from the main memory, instead of waiting for it to be loaded into the cache and then being forwarded, you can give a copy directly to the processor called as the read-through. Coming to the Intel architecture, there are three architectures that are popular: Nehalem, Sandy Bridge and then Haswell. Then for different caches, level 1 instruction cache, data cache, okay, the configurations are given here. For example, it is a 4-way set associative cache, level 1 instruction caches. Data cache has more associativity to reduce the conflict miss. It takes 4 cycles to fetch from this level 1 cache, 16 bytes every instruction. L2 is much larger, 256K cache. Okay. There is also a concept called as the TLB, translation look aside buffer, which can be used, okay, in association with the virtual memory, which we will see later. So with this I will stop my presentation on the cache architecture pertaining to the cache memories. So I will, if you have any questions, kindly post it, or we can have an interactive session. I will take up the questions. What is the main difference between the direct mapping cache organization? Those things I have answered. What is out of order execution CPU? That is, normally the CPUs instructions are fetched one after another, the way they are being written in the program and executed. If it is strictly obeyed in that way, that is, an instruction which is occurring after a given instruction is never being fetched and executed, then it is called as the in order execution. But if a later instruction can be allowed to be executed before a former instruction, then it is called as in out of order execution. This sometimes may be good. If two instructions have no dependency, then to improve performance, you can have out of order execution of instructions. The most commonly used mapping scheme is the set associative. Temporal locality of references is the strongly exhibited one, and replacement policies concern themselves with temporal locality. Size of the block is usually being fixed based on the spatial locality. Do the hit bit has the name in the reference to the cache? There is no separate bit. If there is a hit, then accordingly the content is fetched from the cache. No bit is used to store the hit. How the processor generates the address of what the first byte is to be placed. The processor generates address based on the instructions. Based on what operands are required, it generates the addresses. Is the memory access time for the cache memory access time is higher in the cache memory rather than the main memory? Then why? The main memory uses the DRAM technology, which is slower. Cache memory generally follows SRAM technology, therefore the access time of cache is smaller. Because SRAM is costlier, we cannot afford to have a larger sized cache. That is why we go in for a small sized cache and large sized main memory. What are the methods to optimize cache memory in portable embedded system? Cache memory optimization is a part of the processor design. The architects, okay, who designs the processor has to use the optimization technique and design the processor. The user of the processor have no way of do this optimization. Why does cache drop when we run a program as compared to the value of cache memory when it is compiled? What effect does deleting your cache memory have on the actual data? There is nothing like deleting your cache. You can also use a case where cache only scheme or no cache configurations can be provided by certain processor architecture. If you do not use cache, then the memory references will be, effective access time will be larger. How do I clear cache memory in Google? So see, this is what we are talking about, is the cache memory within the processor. What I mean, you talk about cache memory in the Google is a cache is the web addresses that are being cached, web browsers. They are totally two different caches. Why are the first level caches usually split? The first level caches are usually split because it increases the bandwidth of the cache. Simultaneously, the instruction data cache can be referred. It follows what is called as the Harvard architecture, whereas the level 2 cache is a much larger cache, so it is afforded to store both the data and instructions together. What are the similarities and cache and virtual memory? Now we will see that the replacement policies will have a lot of similarities, okay, when we discuss it in the next lecture, LRU policies and so on being used, whereas the placement policies will differ because the cache is being basically designed keeping the access time in criteria, whereas the main memory is being, or the virtual memory is being designed for the convenience that you need to have a very large memory for the user. So the design criteria for virtual memory design is different from the cache memory design. Therefore the policies will change. Again, the case of how do I clear Internet Explorer 8, that cache is totally different and it has nothing to do with the cache that we are currently referring it. So it is out of scope of the current discussion. Yeah, I think most of the questions have been answered. We will stop at this point. Thank you.